Welcome and thank you for being here tonight. As the world outside goes quiet, we are going to drift to the very edge of our cosmic garden to the invisible frontier that keeps humanity trapped around one single star. Together we will explore why the laws of physics may never let us roam the galaxy the way our stories promised. If this calm science meets mystery journey helps you relax, please gently like this video and subscribe so this little corner of the universe can keep you company at night. There is a frontier that no map records, no satellite photographs, and no telescope resolves, yet it surrounds the solar system like an idea made of stone. It is not a wall of rock or ice, not a ring of debris drifting in slow orbit, not any barrier that metal could pierce. It is a limit written quietly into the fabric of reality itself, a line where familiar dreams begin to dissolve. For generations, human beings grow up inside stories where this frontier does not exist. Starfleets cross the galaxy in a single lifetime. Merchant ships slide in and out of hyperspace. Explorers step from one star to another as if moving from city to city. Whole cultures of fiction unfold inside that assumption that distance is a technical problem waiting for a clever engine. In those stories, space feels like an ocean that patient sailors eventually tame. In the real universe, space behaves more like an abyss. The solar system sits suspended in that abyss, a small garden of light and orbiting stone. The sun burns at the center, planets follow their paths like slow hands on a clock. Comets fall inward and climb back out again along stretched ellipses. Everything looks spacious, open, inviting. From the surface of a quiet planet, the night sky seems generous, sprinkled with points of light that appear almost within reach. Yet every star in that sky is separated from this garden by distances that resist ordinary imagination. The invisible frontier is not marked by signs or beacons, it is defined by numbers. Those numbers appear harmless at first, no more than the product of careful measurement and refined instruments, but they carry a quiet verdict. They say that even the nearest stars are so far away that light itself, which moves faster than anything else permitted by physics, needs years and years to cross the gap. The familiar models of rockets and fuel, of acceleration and arrival, begin to buckle under the weight of such scale. The boundary is not a physical shell around the solar system. It is a region where every tool and habit that once worked among planets fails to extend. Inside the orbits of the planets, travel already demands enormous energy and precise planning, yet remains just within the reach of machines built by a young technological species. Probes fall toward giant planets, landers rest on barren moons, crewed capsules circle a single world. Beyond the last major planet, a different kind of space begins. The intervals between objects swell, the sun fades into an unusually bright star, and the unit called an astronomical distance, once useful for charting orbits, becomes a grain of sand lost in plain desert. This is where the unseen boundary reveals its true nature. It is not a fixed distance that instruments can mark and spacecraft can cross with a single burn of engines. It is the point at which human time, human energy, and human bodies no longer scale with the environment. To imagine that boundary, it helps to freeze the solar system in thought. The planets hold their positions, the stars remain where they are. A single probe moves outward along a thin trajectory carved into darkness. In the early days of its flight, the vastness still feels conquerable. The craft passes the orbit of Mars, then that of the giant planets, and each milestone confirms the narrative of progress. But as the years stretch on, the trajectory becomes a symbol of something else. The probe ages, its power supplies fade, its instruments begin to fail one by one, while the distance to the nearest star hardly changes in any meaningful fraction. The frontier exposes itself not as a place, but as a mismatch between cosmic scales and biological expectations. Civilizations evolve on worlds where a lifetime fits comfortably between sunrise and sunset, where journeys across continents last months or years, where stories compress generations into pages. Interstellar space operates on intervals that dwarf those patterns. The neighborhood of the sun is not a tightly packed city of stars. It is a sparse scattering, more like solitary lighthouses separated by oceans in which no ship can practically sail. The invisible frontier turns the comforting idea of a neighboring star into an almost ironic expression. From inside the garden, other systems glow close together on the sky, yet each one resides behind layers of distance energy limitations, biological fragility, and eroding time. The first awareness of this truth arrives not as drama, but as a slow accumulating doubt. The more precisely astronomers measure the cosmos, the more exact the figures become, the sharper the outline of the prison appears. The frontier is not hostile. It does not push back with storms or shrapnel. It simply lies there in the equations, indifferent and exact, waiting for any species that dares to dream beyond its native star. For a long period, humanity treats those equations as background decoration details for specialists to debate in quiet rooms, while fiction continues to promise effortless crossings. Only when space probes age in real time and mission timelines stretch beyond individual careers does the deeper meaning begin to sink in. The frontier exists wherever hope leans on scales that numbers refuse to support. It is the soft but immovable answer that the universe gives each time. Imagination asks for an easy road between the stars, the subtle boundary where dreams of interstellar empires meet the silent resistance of distance itself. From a distance that no human senses can truly grasp, the solar system looks small against the larger map of the galaxy. It forms a delicate knot of light in one arm of the Milky Way, a single star surrounded by a handful of planets, rings of dust, and scattered fragments of ice. Inside that knot, gravity holds everything together in a long and quiet choreography. The sun rises as the dominant mass, a furnace of fusion whose light and heat define the conditions for every world that orbits around it. Closer in, small rocky planets track narrow paths. Farther out, giant planets with deep atmospheres gather rings, moons, and faint arcs of material. Beyond them, belts of frozen debris stretch outward into a dim frontier. To beings who live on one of those inner worlds, this arrangement appears generous and surprisingly ordered. There is a stable star, a mixture of planets, and a slow rain of comets falling inward and retreating again as if the system were breathing over many centuries. With the help of telescopes and probes, this garden seems rich in detail and possibility. For a long time, that richness feeds a belief that this system is only the first step. If so much structure surrounds one ordinary star, then the rest of the galaxy must overflow with places to visit. The solar system becomes a kind of cosmic backyard, a small familiar space from which a technological species might one day venture outward. In imagination, the planets align like stepping stones leading toward distant constellations. In reality, the shape of the solar system hints at something else. Its outer regions do not open easily into interstellar space. They blur into layers of faint matter that stretch for immense distances yet still belong to the Sun. A ring of icy bodies beyond the orbit of Neptune circles in slow, cold tracks. Even farther out, an almost spherical cloud of comets is thought to surround the system, a shell of frozen fragments held weakly by the star's gravity. Together, these structures extend the influence of the Sun far beyond the last visible planet, turning the system into a kind of bubble embedded in the larger galactic medium. Within this bubble, particles from the Sun flow outward as a continuous wind shaping a region where the star dominates the behavior of charged matter. The boundary of that region, where the solar wind finally yields to the thin gas between stars, lies so far away that even the fastest probes need many decades to approach it. Inside this volume, space is not empty but filled with dust, magnetic fields, and the curved paths of countless small bodies. It is a dynamic environment, yet compared with the gulf beyond, it feels almost compact. Planets, moons, and dust all move in patterns that repeat with almost hypnotic regularity. The solar system functions as a natural enclosure, a region where light, gravity, and material all bear the imprint of a single star. Life, as far as current knowledge goes, arises only inside this enclosure on a narrow band of conditions around one planet. Oceans remain liquid, air stays thick enough to breathe. Temperatures oscillate within a range that chemistry can use to build complex molecules. In that sense, the garden analogy becomes more than a poetic image. The system supplies energy, raw material, and shelter from the harsher background of the galaxy. The star's magnetic field and the planet's atmospheres shield surfaces from much of the incoming radiation. Over billions of years, these factors contribute to relative stability. From the inside, this enclosure can feel like a starting point. From the outside, it resembles an island. Around it stretches a space so empty that a single grain of dust might drift for centuries without colliding with another. The nearest star appears close on a flat sky, yet the volume of vacuum between the two systems could swallow many solar systems without letting their outer edges touch. The apparent closeness of stars on a two-dimensional map is a projection, not a promise. Each point of light sits at the center of its own extended bubble of influence, separated from its neighbors by tracts of space that no current engine can cross within a human lifetime. In such a picture, the solar system becomes both cradle and cage. The same gravitational well that holds planets in safe orbits also binds spacecraft to long, slow trajectories when they try to climb away. The same distances that spread worlds apart enough to avoid constant catastrophe also stretch the path to the nearest star into a journey measured in tens of thousands of generations. The enclosure protects and confines at the same time. It offers moons to visit and dark outer regions to map, yet the step from the outermost debris to the next star is not a simple extension of previous voyages. It is a change of category from local exploration to a scale where time, energy, and matter behave in ways that erode familiar assumptions. The small garden retains its beauty and complexity, but its edges no longer suggest a gateway. They look increasingly like the inner walls of a much larger and quieter prison, one that does not announce itself with visible bars, but with the silent geometry of the galaxy and the vastness that lies between one island of light and the next. The scale of interstellar distance begins with a single number that looks simple on a page and behaves like a vast chasm in reality. A light year is the distance that light covers in a single year while moving through the vacuum of space at roughly 300,000 kilometers per second. when written out as kilometers that span, reaches about 9.5 trillion, a string of digits that does not settle easily inside the human mind. It helps to imagine light itself as a restless traveler crossing the orbit of Earth in a little more than 8 minutes, passing the orbit of Neptune in a matter of hours, and yet still needing year after year to bridge the gap between one star and another. Under that definition, the nearest known star beyond the Sun, Proxima Centauri, sits at a distance of a little more than 4 light years. On a star map, that interval appears as a short line. In three-dimensional space, it is an expanse that makes planetary orbits look like rings drawn on the surface of a grain of sand. Human technology has already tested its reach against that expanse. Probes such as Voyager 1 and Pioneer 10 have been flung outward from the inner system with the help of gravitational slingshots, incremental boosts that add the motion of massive planets to the velocity provided by rockets. Their launch speeds are impressive when measured by the standards of everyday life, yet in the emptiness beyond the planets that speed shrinks into something modest. Year after year, Voyager 1 continues forward, and the distance to Proxima Centauri barely changes as a fraction of the total. After about 4.5 decades of continuous travel, the probe has only managed to accumulate a separation from Earth of a few tens of billions of kilometers a distance that marks a remarkable human achievement and still corresponds to only a tiny part of 1 light year. When this situation is translated into travel time, the numbers become even more stark. At its current speed, Voyager 1 would require on the order of tens of thousands of years to draw near to the nearest star. That span exceeds the entire recorded history of human civilization many times over and reaches backward beyond the first cities and the invention of writing. Another way to frame this scale is to compress the solar system until it fits inside everyday experience. Suppose the distance from the Earth to the Sun is reduced until it can be represented by a single step taken across a room. In that shrunken model, the gap between the Sun and Proxima Centauri stretches to a path tens of thousands of kilometers long. The orbits of the inner planets shrink to slight movements of a foot, while the nearest star becomes a destination that would demand a journey around an entire world. On such a map, the familiar phrase neighboring star acquires a new character. Neighboring here does not mean close enough to visit with a long drive or a slow ship. It means the next point of light after a long stretch of almost pure emptiness. The contrast between local and interstellar scales grows clearer when travel within the solar system is considered. Missions to Mars already succeed by coasting along precise trajectories that take months to complete. Journeys to the outer planets stretch into many years, yet remain within the span of a human career. Those missions require careful planning and durable hardware. Extending the same logic outward to another star multiplies every demand by factors that grow into thousands and millions. A voyage that reaches only the outer edge of the solar system may reasonably return data within a lifetime. A voyage that aims at another star must accept a delay so long that entire cultures and languages might rise and fall while the craft silently crosses the void. Even the speed of light, often treated as an ultimate benchmark of swiftness, reveals its limits when confronted with these distances. A radio message sent at that speed would need more than 4 years to pass between the Sun and Proxima Centauri, turning even the simplest exchange into a slow conversation. Reality is harsher. Actual spacecraft move at tiny fractions of the speed of light, and each additional increment of velocity costs energy in increasing amounts. The figures soon outstrip any resource that a technological civilization can plausibly marshal. These comparisons do more than produce impressive values for textbooks. They reshape what interstellar travel means. Instead of a grand voyage that stretches a little beyond present experience, it becomes a project that brushes against the lifespan of species, not of individuals. The gulf between stars is wide enough that even the hardiest machines begin to look mortal against it. Components age, power sources decay, and guidance systems drift while the destination remains far ahead. In that sense, distance acts as the first and most fundamental barrier in the dream of reaching another sun. Before energy budgets are calculated or biological limits are faced, the raw geometric scale of the galaxy has already passed its verdict in the quiet language of numbers. It states that the solar system is a small warm pocket inside a much larger and colder structure, and that the next island of warmth lies so far away that even light moves there with a kind of cosmic patience. Before any starship can be imagined in detail, the problem of energy steps quietly into the center of the story. Distance alone already stretches the mind, but distance always couples itself to speed, and speed always ties back to fuel. Every spacecraft that has ever left Earth relies on some version of the same basic principle. A rocket moves forward by throwing mass backward. Exhaust rushes out of a nozzle and the craft responds by creeping, then racing in the opposite direction. This exchange is summed up in a relation known as the rocket equation, which connects three key quantities: the speed at which exhaust leaves the engine, the final speed of the rocket, and the ratio between the mass of fuel carried and the mass of the rest of the vehicle. The important feature of that relation is not its algebraic form, but its shape. When a designer asks for more final speed, the fuel mass does not rise in a gentle line. It swells sharply because the connection is exponential. Small increases in desired velocity demand ever larger amounts of propellant. Within the solar system, this already creates strict trade-offs. A mission planner must decide how much mass to dedicate to fuel, how much to instruments, how much to shielding and power systems. Staging partly softens the burden. Empty tanks can be discarded, engines can be dropped once they serve their purpose, and the remaining stack can continue lighter. Yet even with those tricks, chemical rockets only manage to nudge small payloads onto interplanetary trajectories. Extending the same method to interstellar travel forces the rocket equation into uncomfortable territory. If a spacecraft is required to reach even a modest fraction of the speed of light, say 1/10, the fuel requirement for a single-stage chemical design becomes surreal. The vehicle would need to start as a structure in which almost all of the mass consists of fuel, with only a tiny remnant reserved for engines, guidance systems, and any payload. If the craft is also required to slow down at the destination, the problem doubles because fuel must be carried not only for the initial acceleration but also for the eventual braking. That fuel for braking must be accelerated along with everything else at the beginning of the journey, which in turn demands even more fuel at the outset. The loop feeds back on itself until the mass ratios become absurd. The figures grow so extreme that they exceed the total amount of material a civilization could plausibly extract from entire planets. In some illustrative calculations, the required propellant mass for near-light speed chemical travel approaches values comparable to the combined mass of large celestial bodies. At that point, the thought experiment ceases to resemble engineering and begins to look like a quiet proof of impossibility. Even if a society could strip mine its home system, break down worlds into reaction mass, and assemble cathedral-sized tanks in orbit, the energy content of chemical bonds would remain far too low to push significant structures to relativistic speed. This reality explains why practical rocketry inside the solar system already leans away from raw speed and toward efficient paths that use gravity assists and slow spirals. Space agencies exploit planetary motion to borrow momentum rather than fight the tyranny of fuel ratios directly. For interstellar ambitions, the same constraints tighten their grip. Nuclear reactions promise far higher energy densities than chemical combustion, and concepts that rely on fusion or matter-antimatter annihilation appear on drawing boards as possible paths beyond the chemical limit. Yet the rocket equation does not vanish when a different fuel is chosen. It still demands propellant to be carried and thrown away. Raising the exhaust speed by switching to a more energetic reaction improves the situation, but the underlying exponential structure remains. To gain orders of magnitude in final velocity, the system still demands dramatic sacrifices in mass. Some visionary proposals attempt to avoid carrying propellant at all by pushing spacecraft with external sources such as powerful beams of light. In these models, immense lasers or microwave arrays remain near the home star and accelerate light sails attached to small probes. Without the need to haul tanks, the craft can in principle reach a significant fraction of light speed. However, this solution only shifts the energy problem outward. Now, an entire infrastructure of colossal power plants and precise optics must be built to deliver the required intensity over long distances. Keeping such a beam locked onto a sail for years through the tremors of planetary orbits and the pressure of a turbulent atmosphere becomes a challenge of celestial scale, and breaking at the destination without a comparable installation waiting there turns into another version of the earlier problem. Each layer of analysis returns to the same quiet conclusion. The energy required to move macroscopic objects between stars at meaningful speeds does not resemble anything within current industrial experience. It is not a matter of building taller launch towers or slightly more efficient engines. It is a gap between the familiar scale of power production and the output that would be necessary to sculpt spaceflight at relativistic velocities. For now, and for any foreseeable extension of current methods, the rocket equation functions like a mathematical echo of the invisible frontier. It translates the vastness of interstellar distance into impossible stacks of tanks and unreachable energy budgets, reminding every would-be starfarer that the universe prices high-speed travel not in convenience but in exponential cost. Beyond the familiar glare of chemical flames, more refined engines wait in theory sketches and devices. Each of them promises to push spacecraft faster and farther than crude combustion ever could, replacing violent explosions with controlled reactions, focused fields, and carefully managed flows of particles. In imagination, they draw slender arcs between stars instead of slow spirals around planets. When examined closely, however, these elegant designs reveal a hidden kinship with the same limits that bind rockets of the present day. The first advanced concept to step into view is the fusion drive. Fusion is the process that powers the sun, a reaction in which light atomic nuclei merge to form heavier ones and release immense energy. In principle, harnessing that process inside an engine would deliver exhaust moving far faster than the gases from chemical rockets. Higher exhaust speed means more final velocity for the same fuel mass or the same speed for less propellant. Engineers imagine starships whose long spines house fusion chambers, magnetic bottles, and radiators that glow with heat. Pellets of fuel fall into the core pulses of energy trigger fusion, and streams of plasma rush out the back to push the craft forward. On paper, such a drive edges closer to the fractions of light speed that interstellar travel seems to require. In practice, fusion on Earth remains confined to experimental reactors and pulses inside research devices. Facilities still struggle to maintain stable fusion that produces more energy than it consumes. Translating that fragile balance into a compact engine capable of operating for decades in deep space introduces layers of difficulty. The reactor must ignite reliably vent heat without melting its own structure and survive constant exposure to intense radiation. Even if those hurdles were cleared, the rocket equation would still linger in the background, demanding fuel mass and dictating trade-offs between payload speed and range. Ion drives represent another branch on the tree of advanced propulsion. They already operate on some spacecraft within the solar system. Instead of burning a mixture of fuel and oxidizer, these engines strip electrons from atoms of a propellant, creating ions that can be accelerated by electric fields. The ions leave the engine at high speeds compared with the exhaust from chemical rockets, so ion drives use propellant with remarkable efficiency. Their thrust is delicate but can act continuously for long periods. In the interstellar context, however, ion propulsion encounters a different environment. The thrust these engines produce is very small, and the power to drive them must come from solar panels near the sun or compact nuclear sources. To accelerate a craft to a significant fraction of light speed using realistic ion engine designs would require extremely long periods of operation and large amounts of energy. The propellant mass might remain modest, but the time and power demands expand beyond practical bounds, turning the ship into a patient sculpture of metal and charged particles that spend centuries under almost imperceptible acceleration. Another proposal shifts the burden of energy away from the spacecraft entirely. Instead of carrying fuel, the starship unfurls a reflective sail made of ultralight material. Powerful lasers or microwave beams based in the home system shine on this sail. The pressure of light pushes the craft outward. Because the vehicle does not need to haul tanks, it can in principle accelerate to high speeds, using only the momentum transferred from the beam. Concepts such as tiny interstellar probes driven by arrays of lasers arise from this line of thought. Yet even this solution arrives trailing complications. The beams must maintain their focus over vast distances, and the infrastructure must generate power at immense levels. Any misalignment could cause the sail to drift, tumble, or burn. Most critically, once the craft leaves the reach of the home beams, it has no clear way to slow down. Without a similar system waiting at the destination, the probe or ship would rush past its target star at tremendous speed, gathering only fleeting snapshots before plunging back into interstellar space. Ideas to soften this braking problem suggest using magnetic sails that interact with the thin gas between stars, or complex maneuvers around the stellar wind of the destination's sun, but these remain speculative. Some visions of advanced propulsion grow even more abstract. They consider drives that would manipulate the structure of space itself, compressing it in front of a ship and expanding it behind, so that the vehicle rides a wave of distorted geometry. Others rely on hypothetical particles or fields that have not yet been detected. The equations may admit a configuration in which shortcuts appear possible, but the physical requirements for creating such a configuration often involve negative energy densities or exotic matter that no laboratory has produced. In that sense, these engines exist more as thought experiments than as blueprints. When all of these alternatives are placed side by side, a pattern emerges. The details differ. The vocabulary shifts from flames to plasma to beams to warped metrics, but the underlying challenge remains. To cross the gulfs between stars in any reasonable fraction of a lifetime, a civilization must marshal energies and control mechanisms that far exceed anything now available. Each new proposal steps a little closer to that goal, only to reveal another barrier and another dependency on unproven technology. The story of exotic propulsion becomes a catalogue of elegant dead-ends pathways that seem to curve toward the dream of interstellar flight, but ultimately bend back toward the same quiet conclusion. Distance energy and the stubborn structure of physical law conspire to keep even the most advanced engines orbiting inside the invisible frontier rather than breaking through it. Even if engines become more refined and the energy problem bends toward partial solutions, another limit waits quietly inside every potential traveler. The human body evolves under one particular set of conditions on one particular world. It is shaped by steady gravity, a protective atmosphere, and a magnetic field that deflects many of the high-energy particles that sweep through space. Muscles, bones, circulation, and the delicate wiring of the nervous system all grow under those familiar pressures, and when that environment is removed, the same design begins to show fragile seams. In orbit around Earth, this vulnerability already appears. Astronauts in microgravity lose bone mineral density as the skeleton no longer receives the signals that tell it to maintain strength. Calcium leaches out the inner scaffolding of bone thins, and muscles that once carried body weight begin to shrink. Even with careful exercise, the body still interprets prolonged weightlessness as a reason to conserve resources by letting tissue fade. Over missions that last only months, these changes can be partly reversed upon return to the surface. Over journeys that stretch into decades, a crew may arrive with skeletons far more fragile than those of their ancestors, and with hearts that have weakened from pumping in a horizontal environment. Other systems respond in ways that are only beginning to be understood. Fluid shifts toward the head in microgravity, increasing pressure inside the skull and against the back of the eyes. Some space travelers report changes in vision that do not always fully resolve. A vessel that maintains artificial gravity through rotation could mitigate some of these effects, but such a design demands large structures and precise engineering, and it cannot perfectly reproduce the subtle variations of a planetary field. Radiation forms an even more implacable threat. Earth orbits within a cocoon created by its magnetic field, and atmosphere and high-energy particles from the sun are deflected or absorbed before they can reach the surface in high doses. Once a spacecraft leaves that shelter, its occupants move through a region where charged particles and ionizing photons pass with little interference. Each one that traverses the body has a chance to damage deoxyribonucleic acid or initiate changes that may lead to cancer years later. Measurements from probes suggest that a long journey through deep space would expose travelers to radiation levels that significantly increase lifetime cancer risk. Shields made of water, plastic, or other materials can absorb some of this radiation, but adding enough mass to reduce the hazard quickly reawakens the tyranny of the rocket equation. Every ton of protective material must be accelerated and guided along with the crew, and magnetic or electric shields remain untested on the necessary scale. Even if these physical challenges could be balanced with countermeasures, the human mind must also inhabit the journey. Studies of isolated and confined environments provide a glimpse of the pressures that might build inside a starship. Crews in polar research stations and submarine teams in narrow compartments far from sunlight already struggle at times with depression, anxiety, irritability, and conflict. A voyage between stars would amplify each of these factors. Outside every window lies the same unchanging darkness. The destination remains far away beyond any meaningful feedback from progress. The circle of known faces never widens, and the knowledge that no immediate return is possible hovers silently over every activity. To make such travel more feasible, some thinkers imagine ships that carry not only a single crew but entire miniature societies. These generational vessels would host families, schools, farms, and habitats so that the population can renew itself as the voyage continues. The children and grandchildren of the initial travelers would inherit the mission and eventually be the ones to arrive. This model lightens the burden of individual lifespans, but introduces new layers of biological complexity. In a closed population, genetic diversity narrows unless carefully managed, and without enough unrelated individuals, harmful mutations can spread. Maintaining a healthy gene pool over many generations in a finite habitat demands meticulous record keeping and perhaps direct genetic intervention. Ethical questions arise alongside these biological ones. The first generation chooses to board the ship, but the next generations do not. They are born into a metal world between stars, enclosed inside corridors and domes that they never agreed to inhabit. Their sky is an inner ceiling, and their horizon is the curve of a hull. For them, the distant destination is an abstract promise made by ancestors, and some may embrace that purpose while others quietly resent it. The community must prevent despair, rebellion, or apathy from undermining the mission, while also addressing the normal complexities of human relationships. From the perspective of the invisible frontier, these biological and psychological limits form a second layer of containment. The first layer is written in distance and energy. The second resides in cells, bones, brains, and family structures. Even if an ideal engine could be built and powered, the travelers inside the hull remain products of a specific planet. Their bodies expect a certain tug on their joints, a certain spectrum of light in the sky, and a certain richness of sensory input. Their minds expect variation, community landscape, and the open possibility of turning back. When those expectations are removed for years without end, the cost of pushing flesh and thought through the void begins to rival or even surpass the cost of pushing metal. The dream of crossing to another star then becomes not only a problem of propulsion, but a question about how much alteration and risk a species is willing to accept in its own nature in order to slip even once beyond the boundaries that shaped it. Generational ships step forward as a radical answer to the problem of distance and lifespan. Instead of stretching one human life across an impossible journey, the mission stretches itself across many lives. A starship in this scheme is no longer a simple vehicle with a cockpit and a small crew. It becomes a moving world large enough to hold farms, water cycles, recycling systems, schools, and spaces for work and rest. Its interior is designed so that children can be born, grow, form relationships, and age without ever setting foot on a planet. The hull serves as sky, ground, and horizon. Artificial light cycles substitute for day and night, and gravity is supplied either by rotation or by constant gentle acceleration. In such a vessel, the destination star lies not at the end of an individual path, but at the far end of a lineage. From a distance, this concept seems to neutralize the biological limits that stand in the way of long journeys. Lifespans can remain normal. Bones and muscles can adapt to artificial gravity. Education can prepare each generation to maintain engines, habitats, and crops. If the ecosystem is well designed, food and air renew themselves, and the ship behaves as a closed loop. The mission becomes an extension of life on Earth translated into a narrow metal corridor. Yet the more closely this closed world is examined, the more complex it appears. Biological populations in small, isolated habitats do not behave like ideal systems. Genetic drift can erode diversity. If the initial crew is too small, harmful recessive traits may pair up in later generations. Managing this risk requires careful choice of founders and perhaps stored genetic material, each step adding new layers of technology and ethical decision. Social structures inside such a ship must also be more deliberate than those on an open planet. In a sealed vessel, there is nowhere to expand and nowhere to send those who cannot adapt to the mission's demands. Conflict management becomes not just a matter of harmony, but of survival. Leadership systems must stay flexible enough to respond to crises, yet stable enough to avoid destructive power struggles. Culture must give meaning to daily routines and still sustain commitment to a distant goal that no living crew member will see. The ship's library can preserve art, science, and history from its world of origin, but over centuries interpretations of that heritage are likely to shift. Rituals may arise around the journey around the star that lies ahead, or around the memory of the planet left behind. At the center of these developments sits a persistent ethical tension. The first generation chooses to leave a planet and board the ship. Their children do not. They arrive as infants inside an environment shaped by a decision made long ago. For them, the ship is not an adventure, but the entire universe. They may be taught that a blue and green world once existed at the starting point of the voyage, but that world is as abstract to them as distant epochs are to those who remain on a planet. Some descendants may embrace the mission, finding purpose in the idea of reaching a new star. Others may quietly resent the constraints of the vessel and the lack of any alternative. Any attempt to enforce a single narrative about the mission risks breeding resistance. Any attempt to loosen that narrative and allow multiple viewpoints risks eroding the discipline needed to maintain complex systems. Over long timescales, even small deviations in maintenance routines or safety culture can accumulate, turning minor oversights into serious weaknesses that the thin metal hull will not forgive. Psychology adds another twist. In a world where the distance to the nearest horizon is measured in meters, concepts such as wilderness and solitude take on new meanings. Individuals may yearn for open landscapes that they have never seen. Simulated environments can render forests, oceans, and skies, but these representations depend on continuous power and software integrity. They might ease certain stresses while introducing others, blurring the line between experience and controlled illusion. Meanwhile, the possibility of return is absent by definition. Turning the ship around would add as many generations as continuing forward, and fuel reserves would be calculated with a one-way trajectory in mind. Emergency decisions cannot include evacuation to a nearby world or resupply from a neighboring continent. The ship exists alone in a volume of space so empty that no outside help can arrive, no matter how advanced the civilization left behind becomes. From the standpoint of the wider universe, a generational ship appears to solve one equation by writing another in its place. The journey no longer collides directly with finite human lifespans, but it does collide with the difficulties of sustaining biology, culture, engineering, and ethics within a sealed habitat for hundreds or thousands of years. Each new birth aboard the vessel extends the mission and deepens the moral question of consent. Each repaired pipe, updated procedure, and revised rule holds back the slow creep of entropy and social drift for another cycle. The star ahead does not grow closer in any sudden way. It approaches as a slow change in numbers on instruments and as a gradual shift in the stories that the community tells itself about who it is and why it travels. In that sense, generational ships do not break the cosmic prison so much as carry a small echo of a planet's complexity into its quietest corridors, testing whether the patterns of life and meaning that evolved under open skies can survive when they are folded into a moving chamber between the stars. Inside any long-duration vessel, the landscape of the mind becomes as critical as the layout of decks and machinery. Steel, composites, and cables define the hull, but within that shell, thoughts, memories, and emotions move along their own invisible corridors. On a planet, individuals and communities are buffered by vastness. Cities spread across continents beyond every skyline lie plains, mountains, and oceans that no single lifetime can fully traverse. Even for those who never travel far, the awareness that other places exist shapes expectations. A starship removes that background. Its interior is finite, countable, and closed. Every passage becomes familiar. Every door opens onto a space that has been seen before. Outside the hull, the view offers no release, only the same pattern of distant stars pinned to darkness, shifting so slowly that change almost disappears. In such an environment, daily life settles into tight routines whose psychological effects are difficult to predict from planetary experience. Studies from confined environments on Earth hint at the challenges. Crews in low orbit live inside modules only a little larger than small rooms, with no fresh air and no natural gravity. Submariners spend months beneath the surface, cut off from sunlight. Teams in polar stations endure long winters. When the sun does not rise, temperatures plunge and travel outside becomes hazardous. In each of these settings, even among highly trained professionals, certain patterns recur. Sleep cycles drift, irritability rises. Small disagreements sometimes flare into prolonged conflict. Feelings of isolation deepen despite physical closeness. Coping strategies lean on careful scheduling, private time, shared rituals, and regular communication with the wider world. The knowledge that the mission is temporary and that an open planet waits outside acts as a quiet, stabilizing force. A starship, especially a generational one, lacks that reassurance. For those born on board, there is no outside world that can ever be reached. The ship becomes the entire map, the complete sky and ground. Artificial parks, virtual scenes, and carefully tuned lighting can imitate some aspects of planetary life, but the underlying reality remains obvious. All air has passed through filters. All water cycles through tanks. All soil, if present, is measured substrate in controlled beds. The stars beyond the hull are unreachable points of light. Over years and decades, that awareness can press on the mind in subtle ways. Some individuals may internalize the mission's purpose and draw meaning from the idea of carrying a fragile thread of life between stars. Others may experience the vessel as a cage, and their frustration may have nowhere to flow except into the narrow social network around them. The social structure of such a world is delicate by necessity. Population numbers must match life support capacity. professions are tied directly to survival. Every engineer, farmer, medic, and technician carries responsibility for systems that cannot fail. This constant background of importance can heighten a sense of purpose, yet it also increases stress. Mistakes that would be minor on a planet with hospitals, supply chains, and backup infrastructure become existential aboard a lone vessel. The fear of error may push some minds toward hypervigilance and burnout, while others slide into denial or disengagement. Either tendency can erode trust and cooperation. Culture must absorb and redirect these tensions. On Earth, countless cultures overlap, collide, and evolve without central planning. New movements rise, old traditions fade, and diversity persists because there is enough space for many stories to coexist. Inside a ship, cultural evolution unfolds in a compressed medium. Rituals, stories, and symbols may be deliberately cultivated to sustain unity and long-term focus. Festivals might mark anniversaries of departure, successful harvests in hydroponic farms, or key milestones in the journey. At the same time, subcultures can form around different interpretations of the mission. One group may treat arrival at the destination star as a sacred promise. Another may view life aboard the ship as sufficient and question the need to land anywhere. Over generations, such differences can crystallize into quiet fault lines that no engineering diagram anticipates. Psychological support in this setting cannot rely on outside specialists who arrive by aircraft or road. Counseling, conflict mediation, and mental health care must all be provided from within the same closed world. The individual who serves as a therapist is also a neighbor, a colleague, perhaps a relative. True distance between roles becomes difficult to maintain. Archives of recorded knowledge can offer guidance, but they cannot supply fresh external perspectives. Over long spans, new patterns of thought and belief may emerge that diverge significantly from those of the originating civilization, shaped by the continuous presence of the ship and the absence of any other landscape. The lack of a true horizon also alters how risk is perceived. On a planet, exploration can push into new territory while leaving a stable base behind. Expeditions can retreat, regroup, and try again. A starship offers no retreat from itself. Any experiment with governance, technology, or social norms must take place inside the same finite container that sustains everyone. This can encourage extreme caution, slowing innovation, and favoring rigid routines. Or it can encourage dangerous boldness if a faction comes to believe that drastic change is necessary and that the present course leads only to stagnation. In either case, the stakes remain total because there is no unaffected region that can absorb failure. From the perspective of the invisible frontier, these psychological dynamics add another strand to the net that keeps a species near its native star. It is not enough to build powerful engines and thick radiation shields. A truly interstellar civilization would need to understand how to design minds and societies that stay stable, resilient, and humane under conditions of permanent confinement and unbroken isolation. That requirement leans toward altering the very nature of the travelers. It suggests selecting for particular personality traits, training cognition from early childhood, or even modifying brain chemistry to soften responses that become destructive in cramped environments. Each of these interventions raises questions about autonomy and identity. As the thought experiment unfolds, the metal corridors of the ship grow crowded not only with equipment but with dilemmas. The project of crossing to another star demands not just a vehicle but a carefully engineered culture, psychology, and perhaps biology. The cost of failure is measured in entire lives lived inside an experiment that cannot be stopped or reversed. Against this backdrop, the dream of interstellar migration begins to look less like an inevitable next chapter, and more like a narrow path that may require a species to reshape itself before it can hope to step beyond the psychological boundaries written by its birth world. Word count 944. Time introduces a quieter but decisive limit to interstellar dreams, and it does so not only through the obvious fact that journeys of many thousands of years exceed any single lifespan, but also through the way relativity shapes the flow of moments themselves. At everyday speeds, time behaves in ways that match common experience, but as motion climbs closer to that of light, the rules bend. According to the theory of relativity, the faster a vessel moves through space, the more slowly time passes on board when compared with clocks left behind. This effect is not a trick of perception. It is a real difference in the count of heartbeats and in the number of thoughts that fit between departure and arrival. In principle, this phenomenon seems to offer a solution. If a ship could accelerate to a very high fraction of the speed of light, the crew on board might experience only a few years while centuries roll past on their home world. Distances that would seem unsurvivable at ordinary speeds become reachable within a human lifetime as measured inside the cabin. From the viewpoint of those who stay behind, however, the journey stretches into deep future history. The two frames of reference drift apart not only in space but in time. The travelers move forward along a path where their personal timeline diverges from that of their origin world. The frontier that once looked like distance now reveals itself as a temporal cliff. To feel the weight of this effect, it helps to imagine a voyage to a star, many light years away, undertaken at a speed close to that of light. On the ship, gravity may be simulated, systems may function smoothly, and the crew may age from youth into middle age during the crossing. Meanwhile, on the world they left, generations rise and fall. Languages shift, cultures recombine, technologies advance. By the time the ship decelerates near its destination, the society that launched it may exist only as records and archived myths. The descendants of those who remained may look back on the launch as a distant event more like an ancient legend than a remembered project. In this way, every relativistic voyage becomes a one-way trip into the future. Return is not strictly forbidden by physics, but the meaning of return changes. If the ship were to turn around and accelerate back toward its origin, time dilation would again favor the travelers. They might add only a few more years to their lives, completing the loop. Yet on the home world, additional centuries would pass. Loved ones from the moment of departure would long since have died. Institutions and values might have changed. From the subjective perspective of the crew, the round trip might feel like a long but finite adventure. From the perspective of the planet, their reappearance would resemble the arrival of visitors from prehistory. The ship's language might sound archaic, its technology primitive, its cultural assumptions outdated. The returning travelers would be aliens in their own cradle, carrying memories from a vanished world. Relativity thus turns speed, which once seemed purely advantageous, into a source of irreversible separation. Every increase in velocity deepens the divide between ship time and planetary time. There is no way to tune the equations so that the journey is short for the crew and also short for those who remain. A civilization that embraces high-speed interstellar travel must accept that those who depart will never again share the same present as those who stay. This temporal exile adds to the earlier layers of confinement. Even if energy sources advance enough to power near light speed engines, and even if radiation shielding and artificial gravity protect passengers from physical harm, the act of leaving still carries the cost of severing almost all ties to the familiar. Communication across the gap cannot repair that severing. Messages move at the speed of light, so every exchange is delayed by the distance separating sender and receiver. A greeting sent from a ship midway to a distant star takes years to arrive, and the reply requires years more to return. News of events becomes history by the time it is read. Coordinated plans become impossible. The bond between origin and expedition stretches until it becomes a thread of memories and delayed signals connecting two societies that evolve apart. For those who imagine themselves aboard the vessel, this reality reshapes the story. The journey is no longer a bold outward arc followed by a triumphant homecoming. It is an emigration to a future where home has become something abstract, more idea than place. For those who imagine themselves remaining on the planet, the launch of such a mission becomes an act of letting go not only of individuals, but of entire branches of potential history. The departing ship carries away versions of culture, knowledge, and identity that will not intertwine with the main line of development again. The invisible frontier acquires here a temporal aspect that is as absolute as any wall of rock. A species may succeed in pushing some of its members across the gulf between stars in their own brief span of years, but in doing so it fractures its continuity. Parts of that species peel away into separate futures that cannot be fully shared or reconciled. The dream of a unified galactic civilization fades against the strict light of relativity. What remains is a mosaic of isolated timelines, each centered on a star, each unfolding at its own pace, bound together only by faint signals that arrive always late, carrying images from a past that no longer exists anywhere except in memory. Behind distance, energy, and time, another law of nature works without pause, indifferent to plans or dreams. The second law of thermodynamics states that in any closed system, disorder tends to increase. Engineers translate this into practical terms by noting that machines wear out, materials fatigue, and every cycle of use leaves microscopic scars. On a planet, these effects can be managed with constant maintenance, replacement, and support from a broad industrial base. In a lone starship drifting between suns, the same processes accumulate inside a sealed shell with no connection to any external workshop. The vessel and everything within it form an approximation of a closed system. Energy can enter in the form of stored fuel or faint starlight and leave as heat, but the matter that composes the hull, the life support machinery, and the habitats remains largely fixed. Over years and then centuries, entropy expresses itself through slow and varied decay. Metals that hold pressure on day one begin a long journey toward weakness. Tiny imperfections grow, atoms migrate along stress lines, and repeated vibrations encourage microfractures. Welds that once joined plates seamlessly can develop hairline cracks. Seals harden and lose flexibility. Under constant temperature swings and mechanical loads, even the most carefully chosen alloys change character. Electronic systems share the same fate. Components suffer from radiation damage and thermal cycling. Insulation darkens and outgasses, altering the environment around it. Circuits that control navigation, life support, and communication may operate for many years, but nothing in their design guarantees performance over thousands. Each transistor and connection has a finite probability of failure, and when enough elements accumulate that probability, the overall system reliability declines. Redundancy can slow this slide by providing multiple pathways for current and information, yet redundancy itself is made of physical parts that age in the same way. Spare modules stored in racks slowly corrode, and tools required for repair may degrade before they are needed. Biological systems on board also labor under entropy's pull. Closed-loop life support relies on the balance of many organisms, from microbes that break down waste to plants that support oxygen production and food growth. In small ecosystems, the loss or overgrowth of a single key species can trigger cascading effects. Nutrient cycles may drift out of balance, soil chemistry may shift, and previously stable populations may crash. On a planet, such imbalances can be corrected by importing material from other regions. Inside a ship, every correction must draw on limited reservoirs. Introducing new genetic lines requires that they be stored in frozen banks or carefully archived as data, both of which are vulnerable to the same physical degradation as the rest of the hardware. Information itself is not immune. Digital archives of technical manuals, historical records, and scientific knowledge consist of patterns of bits stored on physical media. Cosmic rays can flip those bits, storage layers can wear out, and formats can become unreadable as machines change. Error correction codes can guard against small corruptions, but over very long timescales, the maintenance of perfect fidelity grows demanding. If even a few critical procedures or blueprints become corrupted without detection, later crews may find themselves unable to reproduce essential components correctly. Outside the hull, entropy works in its own way. The vessel moves through a sparse medium filled with dust particles and stray atoms. Each collision, however rare, transfers energy. Over time, tiny impacts can pit surfaces and erode coatings. Radiation from the galaxy gradually alters materials, breaking molecular bonds and creating defects. Shielding can reduce these effects at the cost of added mass, but it cannot eliminate them completely. Small errors in navigation can likewise accumulate. Minute forces from outgassing or uneven radiation pressure may nudge the ship's trajectory, and each correction demands propellant and working thrusters, both of which are finite resources. At shorter time scales, humans treat such degradation as routine maintenance. Inspections, replacements, and upgrades keep aircraft flying and habitats safe. The difference between those systems and an interstellar ship is access to resupply. Parts can be flown in crews rotated, whole structures rebuilt. A lone vessel has no such luxury. Whatever it launches with must serve as a seed for every future repair, substitution, and adaptation. To endure over tens of thousands of years, the ship would need the capacity to fabricate almost any component from raw material and redesign itself as conditions change. In effect, it would have to carry a flexible industrial civilization inside its hull, one that can renew its tools and infrastructure in the face of ongoing wear. The invisible frontier of entropy does not announce itself with dramatic catastrophes at first. It appears as the slow accumulation of small flaws. A valve sticks slightly more often. A crop yields a little less than expected. A file takes longer to open and occasionally shows a corrupted line of text. Each change seems manageable on its own, but taken together over very long spans, they form a rising slope of difficulty. The dream of a starship that glides unchanged through millennia collides here with the reality of matter that always tends toward disorder. so long as the vessel remains cut off from large external sources of fresh materials and low entropy structures, the task of holding decline at bay becomes an endless contest. Eventually, the probability that some combination of failures will exceed the community's ability to respond grows toward certainty, and in that limit, the ship does not so much reach its destination as exhaust its capacity to resist the universal trend toward breakdown, reinforcing once more the quiet message that the universe sends to ambitious travelers about the permanence of the boundaries it sets. The four great limits that shape the dream of interstellar travel begin to align into a single pattern when the question of other civilizations enters the frame. Astronomers look out across the galaxy and see uncountable stars, each one a potential host for planets and chemistry. In a galaxy that has existed for billions of years, it seems natural to expect that many worlds carry life and that some of that life has become technological. Such societies could have arisen long before humanity and had time to spread from star to star. From this simple reasoning arises a quiet question. If the cosmos is so vast and so old, where is everyone? The absence of clear evidence for visiting civilizations or artificial signals is sometimes called the paradox of the empty sky. Radio surveys hear the hiss of natural processes but no unmistakable beacons. Optical telescopes reveal galaxies, nebulae, and clusters, but no visible structures on cosmic scales that can be attributed with confidence to engineering. Closer to home, careful searches find no trace of alien probes, no unexplained artifacts resting on asteroids, moons, or in distant orbits. Space near Earth is busy with human machines, but beyond that local shell, the solar system appears unvisited. Many explanations for this silence have been suggested. Some argue that life itself is rare, that the chain from simple chemistry to reflective consciousness is so delicate that it almost never completes. Others imagine that civilizations tend to destroy themselves through conflict or ecological collapse. Still others consider that advanced societies may simply choose not to expand, turning inward toward culture or simulation. These ideas differ, yet they share a common feature. They do not place the main weight on the structure of physics. When the four limits of distance, energy, biology, and time are considered together, another answer comes into focus. It does not claim that life is rare or that civilizations invariably self-destruct. Instead, it observes that the fabric of the universe may make large-scale interstellar expansion extraordinarily difficult in practice. In this view, many stars may host technological species, but each one finds itself enclosed by the same invisible frontier. The scale of distance forces travel times into spans that strain machines and societies. The energy demands of high-speed flight rise to levels that require infrastructure on stellar scales. The biological and psychological costs of confinement in starships challenge even resilient minds and bodies. The relativistic nature of time transforms every long-range voyage into an act of temporal exile. Under such conditions, the path from a single planetary system to a sprawling galactic civilization narrows sharply. Local exploration within a home system remains achievable. Robotic probes can visit neighboring planets, crewed missions can occupy stations, and perhaps establish outposts on nearby worlds or moons. Telescopes can study distant stars and analyze the atmospheres of exoplanets for traces of life. Yet the step from this kind of presence to true colonization across many systems demands technologies, energies, and cultural adaptations that may lie outside the reach of most societies. If this interpretation holds, the galaxy may be full of civilizations that look outward, dream of travel, and send out occasional probes, yet never cross the great gaps in significant numbers. Each remains bound to its own garden of worlds, limited to the sphere where its star provides power and gravity, holds material together. The silence that humanity detects is then not the silence of absence, but the silence between many islands that lack bridges. Signals may still travel, but they disperse and weaken and drown in cosmic noise. In this picture, the absence of megastructures or alien traffic near Earth does not require catastrophic explanations. It becomes the expected outcome when every civilization confronts the same constraints. Some may try to launch generational ships and succeed in sending small communities outward, but these efforts remain sparse compared with the size of the galaxy. Others focus on perfecting life within their own systems, turning attention toward art, philosophy, or science rather than physical expansion. A few may reach levels of technology that allow more ambitious projects, yet even they must contend with entropy and relativity. The paradox of the empty sky then softens into something less dramatic but more steady. A rare visitor would be a wonder, yet the absence of visitors becomes expected. It is the natural state of a universe in which stars are far apart, resources are finite, and time itself splits the histories of travelers from those who stay. Each technological species stands on its home world, measures the gulf to nearby suns, and begins the same calculation. How much energy is available? How robust can machines and habitats become? How far can bodies and minds be stretched without losing their character? Across the galaxy, countless variations on this decision process unfold, but many of them converge on the same outcome. Civilizations remain near their stars. From this angle, the solar system is not uniquely isolated. It is one example of a common condition. The unseen frontier that keeps humanity close to its sun keeps other species close to theirs. The galactic disk still spins, stars still ignite and fade, and within their thin zones of habitability, complex beings still rise and wonder. They look up at their own skies, listen for visitors, and in most cases receive the same answer carried by the quiet reach of space. Nothing obvious arrives. Nothing undeniable appears. The universe remains vast and luminous, and the gardens of life that dot its arms stay mostly unaware of one another, separated not by malice or neglect, but by the deep structure of the cosmos itself. There is a family of ideas that seems at first encounter to slip past the invisible frontier by changing the shape of the path itself. Instead of crossing the vast distance between stars in the usual way, a traveler might move through a shortcut in space-time or ride inside a region where space itself flows. These concepts appear under names such as wormholes and warp drives, and they rest not in fantasy alone, but in real solutions to the equations of general relativity. They are among the most alluring possibilities that physics has suggested because they hint at ways to reach remote regions of the universe without violating the cosmic speed limit that forbids any object from moving faster than light through local space. The first of these ideas imagines space-time as a flexible fabric that can fold or connect in unusual ways. A wormhole is conceived as a tunnel linking two distant points, perhaps two stars or two galaxies, through a passage that is shorter than the normal route through external space. A traveler who enters one mouth of the tunnel and exits the other could, in principle, traverse many light years in a time far less than the light travel time along the outside path. The mathematics of general relativity allows such structures when extreme conditions are assumed. In that narrow sense, wormholes are not forbidden. However, when these solutions are examined more closely, difficulties appear. Many known wormhole geometries are unstable. They pinch off or collapse so quickly that nothing macroscopic can pass through. To hold them open, the equations require matter with unusual properties such as negative energy density or negative pressure. Ordinary matter from gas and dust to planets and stars cannot supply this. The exotic matter implied by the mathematics has not been observed in nature in the quantities or forms that would be necessary. Quantum physics does allow tiny negative energy fluctuations over very short distances and times, but these effects are delicate and transient. Building a stable tunnel between stars from such fleeting phenomena would demand a level of control over quantum fields that lies far beyond any known or foreseeable technique. Even if a wormhole could be stabilized, other problems arise. The mouths of the tunnel would need to be positioned in useful locations, which implies that one end must somehow be carried or constructed at the destination. That requirement returns the problem of interstellar travel in another form. Before a shortcut can be used, the infrastructure that makes it possible must already span the gap. In addition, some wormhole arrangements appear to permit paths that loop back in time, allowing an event to influence its own past. Many researchers suspect that as yet unknown principles of quantum gravity would prevent such paradoxes, perhaps by destabilizing any wormhole that could be used in that way. Until a full theory exists, these suspicions remain conjectures, and the status of practical wormholes stays in the realm between mathematical curiosity and speculative engineering. Warp drive concepts follow a different route. Instead of connecting distant points with a tunnel, they imagine reshaping space-time around a ship. In one influential model, a craft sits inside a bubble where space behind it expands while space in front of it contracts. The ship itself does not move faster than light within its local region, so it does not break the rules of relativity, yet the bubble can ride the distortion, so that the distance to the destination shrinks while the distance to the origin grows. To outside observers, the bubble appears to cross space faster than light, even though nothing inside locally exceeds that speed. As with wormholes, the mathematics admits such a configuration, but the ingredients are extreme. The original calculations suggested that the energy required to generate a warp bubble of practical size would equal the mass energy of a large planet or even a star. Later refinements reduced those estimates, but they remain enormous compared with any energy that a technological species can harness. The stress on space-time also appears to demand negative energy densities similar to those that trouble wormhole models. These requirements push warp drives into the same category as stabilized wormholes mechanisms that may be consistent with the known equations, but that call for forms of matter and control that have never been seen. Radiation effects add further uncertainty, since the boundary of a warp bubble may behave in ways that concentrate high-energy particles. Any vessel sheltering inside must survive whatever fields and fluxes accompany the creation and decay of the bubble itself. In all of these scenarios, a pattern repeats. Wormholes and warp drives begin as graceful answers to the challenge of distance. They use the flexibility of space-time to avoid the need for impossible rockets. Yet each time a serious attempt is made to translate the equations into hardware, the design calls for ingredients that physics has not confirmed to exist in usable form, or that demand energy on a scale comparable to entire stellar outputs. The universe seems willing to entertain the idea of shortcuts in abstract mathematics while withholding the means to build them with real matter and fields. As a result, these constructions currently lie at the far edge of speculation. They serve as laboratories for testing theories of gravity and quantum fields, and they expand the imagination of what might be permitted in principle, but they offer no clear escape from the invisible frontier. Instead, they deepen the sense that space-time itself participates in maintaining that frontier, allowing just enough flexibility to fascinate while anchoring practical travel firmly to the slower, heavier methods that keep most civilizations near their native stars. The idea that new physics might one day loosen the constraints on interstellar travel hangs at the edge of current knowledge like a faint mirage. Modern theories, from general relativity to quantum field descriptions, have passed every experimental test that laboratories and observatories can presently provide, yet history warns that no framework is final. Each generation of researchers once believed that its equations were complete only to discover wider patterns that required deeper laws. This pattern suggests that the present view of space-time and matter is likely an approximation of something more comprehensive. Within that larger, still unseen structure, some hope that hidden mechanisms exist which could turn the barriers of distance, energy, biology, and time into challenges rather than prohibitions. In this quieter form of optimism, future discoveries might reveal additional fields or particles that can be tapped as new energy sources. They might show that the vacuum of space has properties that can be engineered, or that space-time possesses subtle dimensions that offer shorter routes between distant points. Perhaps gravity itself, now described as the curvature of space-time, emerges from microscopic processes that could one day be influenced in ways not yet imagined. If such possibilities are real, the harsh verdict delivered by current calculations could soften. What looks like a prison today might then be reinterpreted as a hallway whose doors have not yet been found. To explore these ideas, physicists design experiments that push existing theories into regimes where they have never been tested. Particle accelerators collide protons at high energies to search for deviations from known patterns. Space-based observatories watch the afterglow of the Big Bang for subtle signatures that might indicate extra dimensions or exotic fields. None of this work has yet yielded a clear sign of new fundamentals that directly suggest ways to rewrite the rules of travel, but the search continues. Even if such a discovery arrives, the path from revised equations to practical engineering would be long and uncertain. When electricity was first studied, it did not immediately reveal its later uses in communication and power. Similarly, a future theory that unifies gravity with quantum mechanics might initially appear as a set of abstract relations. Extracting from those relations a technique for manipulating space-time energy or inertia on human scales would require generations of work. Each step would need to be tested, refined, and translated into reliable technology. The timescales involved could stretch far beyond the lifespan of any single civilization. There is also no guarantee that new physics will favor ease of travel. It may instead confirm that the universe is even more tightly constrained than current models suggest. The missing pieces might explain dark matter and dark energy without offering any levers that a technological species can pull. They might show that attempts to create shortcuts in space-time lead inevitably to instabilities or catastrophic feedbacks. In that case, deeper understanding would reinforce the invisible frontier rather than erode it, turning vague hopes into sharper recognition of what cannot be done. From a broader vantage, the hope for rescue by unknown laws sometimes acts as a way to postpone hard acceptance. It allows dreams of interstellar empires to persist as a promissory note written against a future that may never arrive. The history of science includes moments where new discoveries transformed capabilities. It also includes many more cases where nature proved less accommodating. No amount of ingenuity has produced perpetual motion or devices that evade conservation of energy. Certain wishes eventually meet firm answers. The possibility of new physics that changes travel conditions is real in principle, but its content and direction are not under any species' control. Meanwhile, the universe continues to operate under the laws that are already known to high precision. Stars fuse hydrogen, planets orbit, radiation spreads, entropy rises. Spacecraft built according to current physics behave as predicted, coasting along trajectories that require years to cross even the inner system. Telescopes reveal exoplanets, star-forming regions in distant galaxies without hinting at easy roads between them. On every scale accessible to direct measurement, the cosmos appears consistent with a reality in which interstellar distances remain large and the speed of light remains an unbroken limit. In this light, waiting for new physics becomes a balance between open curiosity and practical humility. It is reasonable to keep probing the foundations of space-time to search for phenomena that current theories cannot fully explain, and to imagine how any new insights might someday alter the map of what is possible. It is less reasonable to base plans for civilization on advances that have not yet occurred, or to treat the hope of future breakthroughs as a substitute for confronting the constraints that are already well established. A technological species that stakes its survival on speculative shortcuts may find itself unprepared for the demands of life within its actual environment. From the perspective of the invisible frontier, the prospect of new physics does not so much open a door as keep a window ajar. There remains a chance that deeper laws will one day reveal ways to circumvent some of the obstacles that now define the limits of travel. There is also a real possibility that these laws will simply describe the same prison with greater clarity. Until that window resolves into one view or the other, the safest assumption is that the basic constraints of distance, energy, biology, and time will continue to hold. Within those boundaries, a species can still explore, learn, and flourish. Beyond them for now lies only speculation shaped by mathematics and desire. As the pattern of limits settles into view, attention drifts back toward the small sphere where the entire story of one species unfolds. From a vantage point far above its orbit, Earth appears as a pale world wrapped in thin cloud, a bright disk suspended in the dark volume that stretches toward other stars. Against the scale of galaxies, it is nothing more than a minor planet circling a common star, an unremarkable object by mass or luminosity. Yet within the context of the invisible frontier, this modest sphere assumes a different weight. It is one of the few known places where the conditions for complex chemistry, liquid water, and a thick atmosphere align in a stable way over billions of years. Oceans cover much of its surface, storing heat and hosting intricate webs of life. Continents rise with mountains, valleys, and plains that break the monotony of curvature. Air flows and forms, weather clouds build and dissolve, and cycles of evaporation and rain connect sea, land, and sky. The same sunlight that blinds instruments in space filters through this atmosphere and becomes softer, scattered into blue and gold. Here, gravity is not a small centrifuge in a spinning habitat, but a full planetary field that shapes rivers, tectonic plates, and the paths of living creatures. Within this environment, senses that evolved to navigate forest, grassland, and coast find a natural match. Horizons stretch far beyond the reach of outstretched arms. The ground extends farther than any single journey can cover. There are places to leave and places to return to. The walls that shelter at night are voluntary boundaries within an open landscape, not the absolute limits of an enclosed vehicle. From the perspective of the galaxy, such a world is one configuration among many. There are icy moons with subsurface seas, scorched planets near their stars, and gas giants with towering storms. Some of these may harbor their own forms of complexity. Yet, from the perspective of a species that has only confirmed life on this one world, Earth stands as a uniquely accessible sanctuary inside a universe that otherwise appears hostile to fragile chemistry. Radiation levels at the surface are low enough for long lifespans. Temperatures, though variable, remain within ranges where liquid water can persist. The magnetic field and atmosphere shield against much of the high energy flux that pervades interplanetary space. When the limits of interstellar travel are set against this backdrop, the image of the solar system shifts. It no longer resembles a cage built to confine ambition. It begins to look like a rare pocket of stability where improbable arrangements hold for long stretches of time. Within this pocket, there is room for exploration on multiple scales. Robotic craft can visit nearby planets and moons, returning mosaics of alien landscapes. Telescopes on the ground and in orbit can peer outward and inward, tracing the structure of galaxies and the fine details of atmospheric chemistry. Laboratories can recreate extreme conditions for brief moments, testing how matter behaves near the boundaries of current theory. All of this unfolds while the planet continues its slow circuit around the sun, carrying oceans, continents, and the thin zone of air where minds awake. The invisible frontier that keeps travel near the native star then appears less as a punishment and more as an expression of how rare such stability might be. The distances between systems ensure that catastrophes in one place do not easily spread to another, but they also mean that help is unlikely to arrive from outside if a species fails to maintain its own refuge. In that sense, confinement and responsibility intertwine. The same laws that make it difficult to leave also ensure that what happens on this pale world remains largely under the influence of its inhabitants and their star. Seen through this lens, the impulse to imagine distant colonies across the galaxy coexists with another quieter recognition. The most immediate and accessible wonders lie within the reach of this single system. The intricate behavior of weather, the layered history of rocks, the branching forms of trees, the structure of cells, and the patterns of thought are all examples of complexity that have already emerged here under local conditions without any need for interstellar travel. The mysteries that remain unsolved within this one garden, from the deep structure of space-time to the origins of consciousness, are numerous enough to occupy many generations. The pale world becomes a focal point rather than a starting platform, a place where the universe has, for reasons still under study, produced observers capable of reflecting on the vastness that surrounds them. The solar system in turn frames that focal point with nearby laboratories. Mars offers a record of past climates and perhaps ancient water. The icy moons of the giant planets hide oceans that may host unfamiliar chemistries. Asteroids preserve primitive material from the early days of planet formation. Each of these bodies can be visited with journeys that, though difficult, remain within the reach of current or near future technology. Together they form a set of reachable frontiers nested inside the larger unreachable one. To turn back toward the pale world, then, is not to abandon curiosity about the stars. It is to recognize that within the invisible limits exists a domain already rich with unanswered questions and delicate balances. Earth, bathed in the filtered light of its star, circles quietly inside the narrow band where water is liquid and skies can hold clouds. That configuration may be rare on galactic scales. Whether or not the universe permits escape to other suns in large numbers, this world stands as a demonstrably real haven, a small blue exception to the general rule of cold and vacuum that fills most of space. In the quiet aftermath of equations, designs, and distant dreams, what remains is a species standing on a single world under an ordinary star, newly aware of how narrow its practical domain may be. The invisible frontier that once appeared as an abstract idea has taken on detail. It is woven from the sheer stretch of interstellar distance, from the explosive growth of energy requirements with speed, from the fragility of bodies and minds in deep space, from the way time itself bends and splits under high velocity, and from the unhurried work of entropy on every structure that tries to endure. Together, these elements form a kind of cosmic geometry around the solar system, not as physical walls, but as gradients so steep that crossing them in large numbers may be forever unlikely. Yet awareness of these constraints does not extinguish curiosity, it refines it. Instead of imagining crowded armadas between the stars, attention turns to the instruments and methods that remain viable within the given limits. Telescopes spread across mountaintops and in orbit collect faint light from planets that circle other suns, teasing out clues about their atmospheres and possible oceans. Radio arrays listen for natural signals that reveal magnetic fields and charged particles around distant worlds. Spacecraft cross the inner system on journeys measured in months and years, carrying cameras, spectrometers, and seismometers to moons and planets that can be reached without abandoning continuity with home. In this revised picture, exploration does not disappear. It changes scale and emphasis. The frontier between stars remains largely untouched by physical travelers, but information passes more easily. Photons and radio waves move at the speed of light, crossing the gulf where matter may seldom go. A civilization that accepts the practical impossibility of mass migration can still extend its awareness outward, mapping nearby systems, studying the life cycles of stars and tracing the structure of the galaxy. Knowledge becomes the main export and import across the invisible frontier, while bodies and cities remain concentrated around the native sun. Within that framework, the meaning of success shifts. The measure of a species is no longer tied to how many worlds it can occupy with its own descendants, but to how deeply it can understand the environment it already inhabits. The garden of one star and its planets becomes an observatory from which the wider universe can be studied in detail. Local projects such as maintaining climate stability, preserving biodiversity, and developing sustainable technologies acquire a new weight. They are not merely preparatory steps toward a future elsewhere, but central tasks within the only confirmed habitat. At the same time, the dream of reaching another star in person does not fully vanish. It lingers at the edges of planning as a rare, perhaps symbolic undertaking, rather than a path to routine expansion. A few robotic probes may eventually be launched on long trajectories that will outlast the institutions that built them. Such ventures would be pilgrimages rather than migrations, gestures of contact with the larger cosmos rather than foundations of new empires. The invisible frontier then becomes not a line that forbids all crossing, but a region where only exceptional, carefully chosen experiments can unfold, each one carrying the understanding that it will not be repeated casually. Under this view, humanity and any other technological species that share similar conditions occupy a peculiar position. They are both confined and connected, confined because their material presence remains near their home systems, connected because light and gravity pass freely across the spaces between stars, carrying information about explosions, collisions, formations, and flows. From one world, instruments can watch supernovae bloom, galaxies collide, and the cosmic background whisper of its hot and dense origin. The invisible frontier frames that understanding without erasing it. It sets boundaries on where bodies can practically go, while leaving thoughts largely unconstrained. Equations describing the evolution of stars, the dynamics of galaxies, and the behavior of particles near black holes can be developed and tested from within the confines of a single planetary system. In that sense, the universe grants limited physical reach, but generous intellectual access. Whether this arrangement feels like a prison or a privilege depends partly on perspective. One angle emphasizes the impossibility of spreading widely through the galaxy. Another emphasizes the remarkable fact that matter on a small world has, through the slow work of evolution and culture, become able to comprehend the larger structure that contains it. Both views are true at once. The same laws that hold civilizations near their stars also allow those civilizations to discover that very fact. The invisible frontier is therefore not only an external limit, but also a mirror in which a species sees its place. It reveals that the cosmos is immense, old, and largely unreachable, yet also intelligible in surprising degree from one sheltered orbit. With that realization, the final question remains deliberately open. Is the role of a technological species to disperse physically across many suns, or to awaken fully within one system while tracing with instruments and imagination the wider pattern in which it sits? The universe offers no explicit answer. It presents distances, energies, fragile bodies, mutable societies, and relentless entropy, and within those conditions leaves room for choices. How far to try to push against the frontier, how carefully to care for the single garden already held, and how deeply to explore through observation and thought are decisions that remain unresolved, continuing like an unanswered echo under the quiet light of the local star. In the dim hours when night lies fully over the planet, the story of the invisible frontier grows softer at its edges. The great structures of the cosmos remain in place, but their sharp lines blur into a quieter background. Stars still burn, galaxies still wheel through space, and the unseen distances between suns still stretch unchanged, yet the weight of those immensities begins to drift away from immediate concern. The focus narrows back toward a single small world turning slowly beneath its veil of air, and then narrows further still toward one resting body within that world held gently to the ground by gravity and wrapped in the faint warmth of its star. Thoughts that once ranged outward toward distant systems and speculative engines now move more slowly. They trace simpler loops across familiar images, oceans under moonlight, silhouettes of mountains against a fading sky, forests breathing in darkness. The mind that examined equations, distances, and limits lets go of calculation and settles instead into a state where questions remain, but no longer press for answers. The universe continues its vast and patient dynamics regardless, and that realization brings a kind of calm. There is no demand to solve the whole structure, no requirement to cross every gulf. It is enough that awareness has, for a brief interval, touched the idea of those gulfs and then released them. Breathing follows its own gentle rhythm. Muscles grow heavier against the surface beneath them. The constant pull of the planet feels steady and reliable, a quiet assurance that whatever the scale of the surrounding cosmos, this one place offers solid ground and a stable sky. Far above the stars that once appeared as distant destinations become once more simple points of light, part of a silent pattern that asks nothing and promises nothing beyond its own existence. Under that pattern, on this small rotating sphere within a single star's light, consciousness can gradually sink away from waking thought, carrying with it only a faint echo of cosmic vastness and an even stronger sense of local safety, until even those echoes fade into the deep, unmeasured intervals of sleep.